You're gonna have to explain
Yeah, I'm
something.
sorry, man.
It was kind of a little hard for me to grasp on too, but he could be right.
It's a lot of information all at once.
Yeah. I do think like from the limited understanding that I have about light, I do not think that the things you were saying were necessarily wrong. I don't want to jump the shark right away because you were just talking about describing the behavior of light and the certain I would say illusions, right, that we see, because a mirage is like kind of an illusion. It's not really reflective of what reality is, right? But I did hear in the beginning, like, okay, these phenomena about how you're supposed to see things beyond the horizon, or like I believe the type of refraction that should occur on a globe Earth can also occur on a flat Earth. But then, from a critical point of view, I would like to say that, or I would like to question rather, is doesn't that can we not just say that it is not conclusive of whether or not the Earth is flat or round based on that evidence? Because if it can be argued from the globe, and it can be argued from flat Earth, then that's not necessarily excluding one or the other, right?
Not really, right? So this is the difference. You need to, like, okay, so what is a horizon, right? According to us and according to the actual definition of what a horizon is, it's an apparent location, right? It's very important, that word apparent, right? The apparent location where the sky and the ground meet. So depending on what type of weather conditions and temperature conditions and whatnot that you have, right, the horizon's going to shift around. It's going to appear in an apparent location. That's what we see when we look at time-lapse footage, right, of a horizon, right, over the period of a day, right? We see like combinations of these different types of known mirage effects take place, and the horizon will kind of like go up or go down, that sort of thing, right? What can't be explained, right, with these types of mirage effects and whatnot, right, atmospheric refraction, so to speak, is all of a sudden having a horizon that would have to be at 1.2 miles on a globe, all of a sudden popping up 10 or 20 miles away, right, and completely hiding that necessary 1.2 mile horizon and just making it look like it's just flat all the way out to this horizon at, say, 10 or 15 miles out. There's no type of mirage, there's no type of refraction that is described to do that type of thing.
Yeah, dude, this is what I was trying to explain with the rolling pin. We can explain why you might be able to see an object behind a physical obstruction. What we can't explain is how the whole back of the rolling pin can be refracted up into a level surface. Do you understand?
No, not really. If I'm that I was asking earlier about if you maybe or not could have like the thing you were talking about, the phenomenon you were talking about, if it was on paper. If you don't have it, that's fine too. But it's just harder for me to understand what you were talking about earlier.
Not for exactly, because we did talk about a bunch of things, right? So just have a look in the side chat for now, right? I just want to explain just one type of mirage, right? So this is called sinking, right? So there's Oxford reference, right? That's a basic description of what sinking is, right? A refraction effect in which an object normally visible on the geographical horizon apparently sinks beneath it, right? And it happens when you've got warmer air closer to the surface, you know, and then a layer of cooler air above it.
Oh, yeah, I was actually, can I just read it out loud? You don't mind if I read it out loud?
Please go.
Okay. A refraction effect in which an object normally visible on the geographical horizon apparently sinks beneath it. It occurs when air density decreases with. Okay, hold on. It occurs when air density decreases with height at lower rate than normal, or actually increases. Okay, let me just read that real quick again.
Just think of a temperature inversion where the warm air is usually at the bottom, the cold air at the top. Well, then that gets inverted. The refraction gets inverted.
Yeah, look, let me give you a scenario where this would happen, right? So let's just say that you have, during the day in a location, you have 30 degrees Celsius air temperature and 20 degrees Celsius water temperature, right? And then during the night, the air temperature cools down to, say, 15 degrees, right? But the water temperature doesn't cool down, right? Maybe it cools down a couple of degrees or something like that, but not much, right? So the water is warmer than the air, right? So in the morning, right? The air temperature is still pretty cool, right? Because it's cool in the morning. It takes time to heat up, right? So the water temperature is creating a warmer layer of air just above the surface, right? And then it gradually gets cooler as it goes up, right? And that's what Roots was talking about with an inverted temperature gradient, right? And that creates what's called sinking. That's why sinking is more likely to happen early in the morning or during the night, right? Because you have the warmer air going to the cooler air, right? And then later on during the day, you're not going to get that sinking effect, right? Because the air temperature is going to cool up. Going to warm up, right? More than the water temperature, right? So you're not going to have that inverted temperature gradient. You're going to have cooler water and then warmer air. So the air just above the water is going to be cooler, and then it's going to slowly get warmer as you go up, right? Then you're going to get like slightly looming, right? The opposite of sinking.
Yo, guys, I'm on a tree right now. I'm smoking.
Oh, okay, cool.
I thought it was gravity that pulls things down, though. I don't really understand this.
Yeah, it would have to be if the Earth was close.
Right, so gravity pulls down the light to show you what's behind the horizon.
No.
DJ,
Look, one second, I'll just answer that really quick.
Yeah.
Even according to the globe side, right? Like gravity isn't pulling the light down, right? And even if I granted you that claim that gravity does bend light slightly,
Nobody cares, bro.
Over that distance of say 10 miles, it would be like the millimeters of difference. It would just be insignificant. You wouldn't have to factor it in, right? So according to the mainstream, what affects light bending is like temperature gradients, because what happens when you have
Einstein?
No, that's completely different. That's completely different.
Einstein is considered to have like a description of what gravity is. It relates to. I'm just quoting things, right? I'm not making claims, but it relates to mass and space-time being related to one another in a way in which they affect one another. That's a description being used, and that gravity is being, or at least that mass curves space-time, and that the phenomenon that we consider as gravity is some interpretation of curvature of space-time, right. Which is counterintuitive by itself a little bit, but it could make.
Well, yeah. So a light source. Let's imagine a light source behind a planet, and you have a planet in the way. Because of the curvature of space-time, the light is going to follow the curvature of space-time, bend around the planet, and meet your eye. 1919, right?
Right. Look, we're not talking right now. We're talking about we're talking like long-distance observations on a small scale. Right? So you wouldn't have to. That would be a different topic. What you're talking about now, right?
You gravity could even affected it there.
So you could look it up. Right, I've looked it up. I've had globe earthers ask that exact question before. Wouldn't gravity be bending the light? Right, and you could even look it up on ChatGPT. Say how much would gravity bend light over 10 miles? Right, it'll say it's basically nothing, like an insignificant amount. Right, and it'll go on to tell you that it would be atmospheric refraction that would be the cause of why light's bending over that particular distance. Right, that's what the mainstream response would be. I would be telling you the same, even if I was a globe earther, right? Because that's just the mainstream way it's explained.
DJ, I would like to say, I would like to conclude it for myself. I have to go right now, but I would say that when we're talking about light, this is something that I found very intriguing as someone who doesn't necessarily believe that the Earth is flat. When I was watching the videos about objects that are supposed to be not visible beyond the horizon, I found that very intriguing, and I was very interested in what the people who had probably more knowledge and not affectionate towards flat Earth had to say about this. I looked it up, and I think the things you were saying about light, I don't really see any holes in that explanation that you gave. I will say this: I fail to understand how this correlates to proving that the Earth is flat. I don't know if there's other pieces of evidence that need to be correlated to one another in order to come to that conclusion. Does not necessarily mean that what you were saying is wrong, but it's just how it comes to me. I will say this. I I could see how it is inconclusive about proving whether or not the Earth is round or flat, and you may disagree or agree on that.
Yeah, that's fine. When you have more time, like we'll spend like an hour going over actual practical demonstrations and mainstream citations, right, to go over this in more detail. But yeah, we don't use these long distance observations to prove that the Earth is flat, right? This
Even
is
as someone,
us.
yeah. Even
This
as
is
someone
us.
doing all work. Oh, sorry. Yeah, go ahead.
Well,
No, I
this
think-
is us. Well, let me just finish this quickly.
Yeah,
right?
sure, yeah.
This is us challenging the essential features that must be there if the Earth is a globe with a radius of 3,959 miles, right? It would have to have a certain amount of curvature over distance, and it would have to have a geometric horizon at a certain distance. Right, so this is us directly challenging that, right, rather than using this as flat Earth proof, right? And then you could kind of like, okay, so
think the challenge is justified.
if these necessary things for a globe to exist aren't there at all, right, then that's kind of like the default position that if there's no curvature over a surface, the surface isn't curving, right? It's therefore flat. Right, so I mean, it kind of is flat Earth evidence, but we're not using this as like this proves the flat Earth, right? This proves the curvature rate and the geometric horizon claim.
Yeah, when you mention the curvature rate, it is not something that I necessarily question. I think when we're looking at where we're supposed to see the curvature from these from the parameters from observer on a circular object or like a perfect circle, for instance, I do not think that these theoretical how do you say it? Yeah, these theoretical measurements necessarily correlate to or translate into reality. I mean, I think it requires more accurate simulation of what the circumstances are, because apparently we are still measuring light and we're not just looking at a calculator and seeing things, the numbers that it shows. But even like it still doesn't mean that it's totally not suggestive at all. But I think it requires connecting the dots. And as of right now, I'm basically repeating what I said. Is I still haven't really understood how this correlates to flat Earth. But like you said, maybe there's something we should look at later.
Or when over time, right? Like you got to learn all the different types of mirages, exactly how they happen, and how none of them explain these long distance observations that we're doing consistently, right, in different places, different locations, different weather conditions, right? Then we've got laser tests over and over and over again, impossible on a globe, right? And there are globers out that try to explain it, but they don't have a very good understanding of how their own mainstream explains different types of mirage effects, what atmospheric refraction is, what refraction is in general, what refraction isn't, what type of refraction doesn't apply to these observations, right? It gets into like technical detail, right? And all of this, all of this can be easily explained. Even if I was a globe earther, right, I would still be using the same argument that certain observations of, say, ships over a horizon, right, or claiming a geometric horizon with a particular video or something like that isn't a good proof of the globe. Because it can easily be explained right? It can easily be explained just with these different mirages, right? And different things that we could go over. And it can be recreated on small scale flat surfaces, right? The same thing, showing that it's not exclusive to a curved surface.
Right. I don't want you to go into any further than is necessary, because I have to go right now. So I think this is more useful for when we talk later, and I have a little more time on my hands, right? But no, thanks for your time, and thanks for addressing.
Well, dude, before you go, can I just leave you with this context a little bit?
Yeah, of course.
The reason why we approach a subject like this is because the globe is the positive claim. Because we don't experience naturally any of the claims of the globe has that burden of proof. So when you approach this, it's like, okay, the claim is the surface is curving. and the surface is rotating. So you have to look at this, right? These are the claims. Where can we find the evidence? If there is no evidence, then the claim itself is false.
Yeah, when it comes to providing evidence for stuff, there's ways that are considered in general to be accepted. I think a lot of us would accept, empirical evidence, for example, right? But yeah, I don't really. But that is also like a way that is empirical evidence is also a thought out way of like determining what is considered to be objective reality, and therefore this is very far-fetched, by the way, because you can't really like argue with some of these observations that you see, right? But I can't figure out the point I was trying to make, but yeah, when it comes to assessing evidence, is also something that I want to talk about, like how we should go on about these things. But yeah, I don't hear the things that you're saying that are necessarily wrong or anything like that. So. But yeah.
Yeah, I just wanted to sort of, reframe it as, look, this is the claim. It doesn't match your reality. It doesn't match what we observe in nature. It doesn't even match like the laws of nature, the whole claim itself. So this is how we need to look at it. If this is going against everything we can prove and test, then, and there's no direct evidence, then it is nothing more than a belief at this point. And that's
I get that. And I believe the burden of proof lies with anyone claiming anything. So not just flat Earth, also globe Earth. And what we did the past time was talking about the object disappearing or not disappearing behind the horizon and describing the behavior of light. I thought that was a very useful thing to do when you're assessing like certain when you're assessing certain phenomena and you're trying to describe them objectively, right? So I think that's a very good thing to do. But yeah. All right, I'm gonna have to go. I'll see you guys later. Take care.
All right, bro.
And,
you take care, bro.
All right, see you later.
Yeah, come back.
See you, man.
See you next time.
Catch you later. Yeah, Kemba, you were...
Back to gravity, guys.
Oh, go ahead, yeah.
You guys are gonna have to.
I'm going to have to mute up.
You guys don't believe in gravity, I heard, right?
Yeah, gravity, right? So, you need to have gravity to have a globe, right? So if you want to have a globe Earth, you're going to have to defend gravity to the death, right? Because no gravity equals no globe Earth model at all, right? But you'll find that on a flat stationary, right, enclosed system, right, kind of like what we observe, like what we all observe and experience in reality. Right, you don't necessarily need gravity like that, right? So things will rise or sink depending on their density, depending on their density in relation to the density of whatever the surrounding medium is, right? So the surrounding medium for most, for everything basically in the outside world is air, right? So air is a very light medium, and most things will sink through air because they're more dense than air. Right, but not everything's more dense than air, right? You've got like a helium balloon, for example, right? You let go of a helium balloon, it doesn't sink, it goes up because it's less dense than the air, right? If it were more dense than the air, it would sink, right? Like a tennis ball, right? You lift it up in the air and you drop it, it's going to go down, it's going to sink. But if you release a tennis ball in a different medium, say a tank of water or something like that, right? The tennis ball is going to go upward because it's less dense than the medium, right? So it pretty much explains, right? Like relative density explains why things rise or sink, right? In all of nature, right? Now, nothing actually just rises or sinks by itself, right? It would need to be displaced first, right? So a rock sitting on the ground, for example, will never move. Unless some outside source of energy is exchanged to displace the rock, right? And just say you come along, for example, right? You lift up the rock, right? You had to exchange some of your energy to displace the rock, right? And you've put it out of equilibrium, right? It was sitting on the ground because it's more dense than the surrounding medium, right? And it's sitting at the bottom of the medium, basically, right? You've lifted it up and you've displaced it, and when you release it, it's simply going to sink back down again to re-seek equilibrium,
Or
right?
gravity.
No,
Gravity
no.
takes it back down.
Right. No, it's more dense than the air, right? Just like the helium, like you do the same thing with the helium balloon, right? It rises, right? Because it's less dense than the medium, right? Here's an example, right? You could get an egg and put it in a glass of water, fresh water, right? It's going to sink down to the bottom of the glass, right? You could then add some salt into that water, right? And then the egg's not going to stay at the bottom of that water anymore, right? It's going to come back up and then it's going to sit at the top of the glass, right? All you've done is manipulate the density of the medium, right? And you've been able to manipulate the what the object does, whether it sinks or rises.
Oh, you added salt, man.
Yeah, you added salt, which manipulated the density of the medium, right? Now the egg isn't more dense than the medium, right? Now the egg is less dense than the medium, right?
Yeah.
So it doesn't sink. Now it rises, right? The only thing you manipulated was the medium.
You added mass. So you added gravity because you added mass and gravity to the cup.
You didn't
Now
add
the egg
mass.
starts to float.
You just changed the density.
You added salt, right?
Yeah, you changed the density of the medium. Yeah.
Which is mass divided by volume. So to change the volume or change the mass, right? Well, if you change the volume, it doesn't change the density.
You're not changing the mass. You could take some of the water out. You know, if you want to put in 10 grams of salt, just take out 10 milliliters of water, right? It's still the same weight. Right, so you're not really adding. That's not.
Yeah, but it's not the weight per unit volume, which is density or mass per unit volume.
Why do you think a helium balloon goes up and doesn't sink?
I don't know how to defend that as a Glover. Hold on. Let me think. What did the Glovers say? What's the traditional Globier answer for this shit?
They're gonna say.
Someone help me out.
They're gonna say that. I mean, and it does. It's along the lines of what DJ's already saying, that when you have something and its displacement, that's going to make it's going to fill the space where it's less dense. So it's going along the lines exactly what DJ is saying, because I mean, picture like a balloon in the air, and obviously the air is certain weight, and then all of a sudden you fill it with helium, which would make that balloon less dense. So then the constant pressure, which is we talked about earlier, to get pressure you have to have a container, but because there's that constant pressure, then when you create something that's less dense, it's kind of like taking a basketball to the bottom of the pool and then letting it go. Like that basketball is going to shoot up out of the water.
I think I get. So you're saying the pressure from the skin of the balloon that's being exerted on the helium, what was it, or hydrogen, whatever, makes it go upwards?
Because the helium in the balloon is less dense than the air that you're filling the balloon up in. So
and why would it go upwards if it's less dense?
Because the pressure that's being pushed like to the surface of the medium, like DJ is explaining, how when you hit something at the bottom of the medium and it can't go any further. But like you said, if you were to, like, let's say, take a balloon, fill up with helium, well, it's going to be less dense than that surface pressure, so it's going to go up because that pressure is filling in where it's less dense, so it's like squeezing it out, if you will, or squeezing it up. And it's just like I said, it's just like if you take a basketball to the bottom of the water. Well, the basketball is filled with air, so, and that air is less dense than the water. So the water's going to rush into that area that's heavier than the basketball, and it's going to literally just shoot it upwards. And you have to realize that pressurized system, like all the physics about it, is only because we are in an environment that is contained in the grand scheme of it all. That's the only way we can have these things going up and down, is because it's having to do with pressure, high
we're contained.
systems,
So we went from a helium balloon to helium Earth. Like we're contained now. How does this work?
No,
We're just talking about
the entirety of this place that we live is contained somehow, some way. Has to be, because that is
gravity.
No,
gravity contained.
So
the,
the reason why when you say gravity, it comes with baggage, and that's why when someone that believes the Earth's a globe and they say gravity, quickly we are quick to defend against that, because when you say gravity, you are probably thinking of an outdated version of mass attracting mass. So a ball has to be attracting to a
mass
ball.
Mass bends the space.
Yeah, I know that's the claim.
I'm well educated.
I know that's the claim. No, well, you can be educated. You can take a test and know all the answers to Marvel Universe, but it doesn't mean that is our reality. So, like, if you are saying because this person said this, that, and that because of something they saw up in the sky, that's not explaining the antecedent that has to be in place, that there is a container, and then but you're jumping to, oh well, there's this thing called gravity because balls attract balls, but that's where we're like, nope, that's ridiculous, because is there this pressure upon us that's making things go up and down? Yes, we know that, but not in the sense of you were saying, oh well, it's because it's a globe and it has gravity, and gravity holds all the oxygen and all
I never claimed globe. I just said gravity.
Okay, okay, that's fair.
All right.
Apo, did you hear what he just said? You said that he's thinking about the outdated gravity. So he said that no. I'm talking about the mass creating the curvature on space-time. And he asked you, can you disprove it? No, there is no reason to disprove something that have never been proved first.
Thank you.
That's
right.
Well,
thank you. I know it's not proven. Okay, appreciate that honest answer.
At least you know that it's not proven. At least you know it's not proved.
Yeah, but, of course. I know it's I know it's quackery, but I know it's serious.
Yeah, look, bro. Look, the simple answer to your question was you asked why do the globers claim why things go up? They'll just say because of the buoyant force, which is basically including gravity in the formula. Right, so things will go down because of gravity.
There, DJ.
Go up. Yeah, things will go up.
You know exactly what I was going there.
Yeah, but yeah, look, that's the thing, bro. Like, gravity's unproven, right? It's just something that has to be there, right? Like if you ask the professionals, right? I got video clips of this. They're asking them, what is gravity, right? And they say, we have no idea what gravity is. It just has to be there, basically, right? We can observe the effects. We can't prove it.
Dark matter.
Right? We don't know what it is. We don't know where it comes from. But yeah, it has to be there basically to have this model of the Earth, right? That's the mainstream model. But yeah, it's unproven. They don't know what it is. They don't know where it comes from, right? They can't find any curvature. They can't prove any motion.
But you know my proof to Einstein, right? If you really want to go down that road, you know what I'm talking about, right?
Oh, well, there is no scientific proof. I mean, what? Of
course there is. I mean, I don't want to pretend like it was legit. Of course, it was bullshit. But you should know this one: special relativity, the Arthur Eddington, 1919 eclipse. No. Yes.
Mm-hmm. Yeah.
Are you aware? So you are. But weather reports on that day were cloudy. Anyways.
Yeah, but what's your position on this topic, right? You seem like you were just asking general questions, like you've never looked into it before, but now you seem like maybe you have looked into it.
Let's see. My general position. I am definitely a flat earther, and I was just trolling you guys. That's for sure.
I knew it. I fucking knew it. I knew it, bro. I was like, wait, I talked to him the other night. He's a flat earther. What the hell he's talking about? I'm thinking, and I saw Pumpkin in here too. I'm like, it can't be. You know what I mean? I knew it, bro. But I didn't want to say anything. What's up, bro?
That up for quite a long time.
I know, man. What I do. I didn't want to. I couldn't defend that bullshit. Like at some point, I'm like, I don't want to defend a helium balloon going up, man. It's like I'm not gonna.
You can't defend.
I want to. Well, the only thing I was thinking of is taking them. Oh, you know, well, the gravity's in the equation. That's exactly where I was going to take it. Because that's it. I don't really have shit here. If I go that it went up because due to the thermal energy, I'm actually speaking legit here, so I can't do that. I gotta, I was trying to figure out a troll that's, not true. Like, yeah, I failed.
Classic.
There's
Is there any glober with us now? Because I want to talk about something, but I don't want to give them anything to use. I don't want to help. So they want.
I don't think there's any Glovers in here.
So nice. I have a.
We have Globies in here. Nor? Maybe Nor?
I have a small issue with the relative density that I still try. I can't explain the shit of it completely, but I try. So, have you heard about what happens to the helium balloon inside the zero-G plane?
Mm-hmm. Yes.
So, okay, nice. What would happen if you place a nice where the here is the problem. So that's the problem. Why the balloon?
What happens to it?
Is not going. So the helium balloons in zero-G planes doesn't go up.
Mm-hmm.
It stays where it's at.
Yeah. What's the problem? What's the issue? If we use the formula of relative density and Archimedes' principle, we should see the helium balloon go up.
Well, not really, right? Because what happens when you have that zero-G parabolic flight, right? So it temporarily removes the vector, right? So that while you're in that state, right, there isn't an up and down, right? The vector temporarily goes away. It's not until it balances out again, and then you'll have that up and down vector again.
So now we go back to the vector, because we can talk about the vector with the density and buoyancy, so things go up and down because of relative density. Now, if you eliminate the vector, which is not created by the density and buoyancy, we will have an issue. So you will have to create the vector. So whether using the real vector created by electrostatics, or you will let the glober claim the gravity.
Well, let me explain something to you though. So when you take a balloon and you put it in a pressurized system, it's the same thing that McToon did yesterday, and he looked like an idiot live online. If you take something and you create your own pressurized system, like all those things that are happening out here, you kind of made like a mini you in there. So like to say, why is a helium balloon like stay in this environment in the plane that's enclosed and pressurized? Well, it's the same thing why the helium balloon will go up until it finds its medium within our pressurized system. So like the question should be, well, why is the helium balloon like hitting the top or hitting the bottom. It just rests in the middle. Well, that's because it's the same thing equivalent to what's happening in real life here. This is a pressure system. And then if you create like a smaller pressure system, like the helium balloon is going to do the same thing within that pressure system. So it's just, and talk about those zero G things, like they are literally just like flying, right? And then all of a sudden they're in this state of like, whoa, we can float now, whatever. But technically they're just falling with that plane, and they're creating the effect of weightlessness, quote unquote, but you're still confined. So it's almost like equivalent to, like, imagine a roller coaster. Well, when you're on the outside of and you're sitting in the cart and you're going down, you're gonna feel you falling like 6 stories, to a drop. But if you were to put yourself in like an enclosed pressurized system falling 6 stories, you're gonna start to float. You're like, whoa, and then you see the videos where those parabolic flights, like that they do training in, those vomit comets that they do training in, you see like they've slammed against like the side when like that little drop ended, and they just weren't prepared for it. So it's just all physics, bro. It's really easy too. It's simple if you really think about it. I don't know why Globers try to make it really complicated. Well, they probably have to, because it puts it out of your
He's got a
reach
really
to
good question,
understand.
though.
What?
That's cool. I like his question, because so if you have a body or a system, call it system A or whatever, just draw a circle on your piece of paper, right? You got 2 forces acting upon it, 2 vectors, one down, mg, w, weight, yeah, and the other one is F of B, buoyant force. So it's when those 2 are imbalanced, the object does not move. Okay? If you add thermal energy, let's say it's a hot air balloon, you add thermal energy, the density decreases, it's definitely going to go up, because the 2 forces are no longer equal, right? And the
Right.
buoyant
Yeah,
force
you
is
can
greater
manipulate it with
than the other
temperature.
force.
Right.
Well, this other force is what he's really talking about when he took it to the vomit comet, right? It's like, why is everything nullified right here? Why isn't
Yeah.
it? Because if you release it, it should go to the top of the plane. But in that state, it just hovers. Why? I'm intrigued. I don't know why. Like, this is
like
cool.
DJ said, that shit will take away what we call a vector, that downward vector or upward vector. For the thing that is more dense, it will go down, and less dense will go up. We understand that, but if you eliminate that vector inside the 0G plane, so those things will not go up and down. So there is something else.
Well, I would just say it's an
I
equalized.
like your point, man.
Yeah, I totally get it. It's just more like it's an equalized environment, as far as like he's talking about those two formulas that are kind of like fighting against each other, and then they equalize, they like neutralize, because you have both of them acting upon you. You're gonna kind of find your equilibrium in the middle of that. I don't know, like if that doesn't suffice, then like maybe.
In reality, just to be precise, what will be equalized there when the 0G plane is falling? So there is a movement. That's the thing that is changing for me. There is a movement of the medium itself and the helium balloon inside the medium. They are
What's the same reason?
down. But the problem,
okay,
just listen. The density didn't change. The helium inside the balloon and the rubber balloon, their density didn't change. The air around the balloon, its density didn't change. So there is no equilibrium. Like we were talking about the salty water and the egg. If you make the equilibrium between the salt and the density of the egg, so the egg will just levitate inside the medium, will not go up or down. So that shit, I can understand it. But
well,
it happens.
You don't have to even say. You don't hold on, Necros. You don't even have to use a helium balloon, though. You can use anything, like anything in that framework. So you don't have to say, why does a helium balloon just float? Well, everything would float in that state, in that in this flight.
the
Until
denser
it comes
object,
to
the denser object will not go down. The less dense object will not go up. So that's why the helium balloon behave like the same as the human and the heavy objects inside that 0G plane. So they don't follow anymore that vector. I could understand the thing with people inside the plane, so the denser objects, but I never try to think about the less dense objects. I just started thinking about that. Because I could say that, yeah, the denser object or the human inside the 0G plane is falling with the same velocity of the plane itself. So he won't be able to accelerate more than the plane to reach the ground, to reach the floor of the plane. So to be able to stand up, because he can't have more velocity. The only moment where he can do that if he push with his feet at the roof of the plane, so he will just go to the floor of the plane. At that moment, it's possible.
Okay, so what happens when, think about this, what happens when the plane levels off and it's no longer doing its little parabolic, like little roller coaster action? What happens when the plane levels off and now they're going to go land and they're done with their training? What happens to that helium balloon? Is it still just floating right there in the center? Or is it on the ceiling of the plane while they're all sitting down with their seatbelts? What do you think?
I agree that the less dense object at that moment when the plane is leveled or when
it's going to be on the roof, right? The cabin?
Yeah, the helium balloon will go to the roof and the people will just settle down.
Right. So that's why I'm just saying, I'm just trying to point out, like, anything when you're in that, 0G, they call it, environment, it's really, you're just falling with the plane. But when you're in that environment, yeah, that's when things do weird things. They're not stuck at the top of the cabin because you're falling with it. So it's like he's saying, for momentarily. Matter of fact, you know what that reminds me of? Have you seen, like, when they drop a slinky in slow motion? That's something I've been wanting to talk about personally. That's pretty cool.
Yeah, I've seen it.
How the bottom of it doesn't move at all.
I can understand that. I can understand the physics of how it works. I can understand it's because that's coil thing. It has that when it's stretched and you release it, it has that natural thing on it because of that metal or plastic that it used. So it wants to come back to its normal form. So there will be the top part that will fall, but the bottom part will not fall or move because the middle is attracting that downward part. So it will not fall till a certain moment with that energy because that coil was stretched.
Isn't that pretty interesting though? How, like, it just floats in the air for like a split second.
Yeah. It is
pretty interesting. Like, I don't know if you guys ever watched that, but that's freaking cool as fuck.
Yeah, anyway. It is literally interesting. But like I said,
I think observations like that of things doing, like this weird, like, wait, what? Like, that's not supposed to be happening. But that's just because in the laws of, that man has, discovered, written down, observed, whatever, agreed, whatever. Like, they realize, like, okay, certain things happen when certain things happen. And like the balloon floating in this 0G environment, they call it, like, this, it's a result of, everything in the way it's moving. Or counterbalancing, should I say? And it's kind of it's something that just is created. That environment creates that observation to look like, well, what the hell? Why is that thing just floating there in the middle? And then you can say that about a human. Wow, why is that human floating above his seat? He didn't have a seatbelt on, now he's floating. Well, that's kind of like what happens. Same thing would happen on a roller coaster.